Good afternoon, everyone. My name is Vincenzo Scotti. I'm from Politecnico di Milano, and today I'm presenting the work I did with my colleagues titled Def2Vec Extensible Word Embeddings from Dictionary Definitions. I worked with Irene and Professor Tedesco. Irene was a master student that we followed during her final thesis to graduate, and this is the result of her work. Today we're talking of basically word embeddings, which are vector representations of words holding semantic meaning. I know that this is redundant knowledge and many of us already know, but I just wanted to point out a few things about them. So ideally in these embeddings, the position of words in space is connected to their meaning, and the relative position of the words is connected to their relation. For example, we can see here that the same vector difference between king and queen occurs in men and women. So we have masculine and feminine generated words. We also have grammar concepts like verb tenses. We can see that in working and work does, swimming as well. These are all features that occurs in word embedding models. Interestingly, in some cases, they also record some facts like the country capital relation, as we can see in the third picture. To build up these vector representations, so to extract them from a corpora of text, usually we analyze the word co-occurrence statistics. There is the famous quote from Firth from 1957 that says, "You shall know a word by the company it keeps." So this started a long sequence of model definitions and building that first started with unsupervised learning approaches like latent semantic analysis to produce term document matrices and extract embeddings from there, mostly used in information retrieval. Now we have more sophisticated approaches based on self-supervised learning like Word2Vec, GloVe, FastText, and similar. All these models are actually quite limited, despite they are very powerful, because they mostly learn a linear dynamic. They produce representations that are independent from the context, so from where a word actually appears, and they cannot manage auto-vocabulary tokens. Now, there is an asterisk there because actually FastText can manage to some extent this concept because it also builds its representation from subword pieces, so from character level embeddings too, not only from the embedding of the single word. And right now, I mean, in the last 5 to 6 years, we all see these problems, let's say, disappear because there are deep language models, now LLMs, that can deal with all these kind of issues. But the deep language models are very power and data hungry, so you need a lot of data for pre-training, other data for eventual fine-tuning, and it's not always possible. While word embeddings are still very, very compact and used even outside the NLP community. For example, they are still used in medicine or sometimes also in material engineering. And with our work, we decided to focus on the issue of dealing with auto-vocabulary tokens. So what we decided to do was to do a step back and get back to word embeddings and to latent semantic analysis. But what we did was to exploit more structured information when we built our term document matrix. In fact, we started working with term definition matrix instead of a term document one. The idea is to, instead of using generic documents and counting the words in them, is to rely on the actual word definition from a vocabulary, from a dictionary, to build the embedding representation. Differently from what we used to do, where we had like rows containing the statistics of a single word, in this case, we decided to build the matrix, putting in each row the TF-IDF definition, the TF-IDF embedding of the matrix, and then we applied LSA, basically singular value decomposition, to the resulting term document matrix that here we call term definition matrix. The point is that the rows in the term definition matrix are basically the TF-IDF vectors of the definitions, and when we apply the LSA and we factorize this huge and sparse matrix, we obtain that one of the decomposition matrices is actually a matrix holding embeddings. So from the one-hot encoding definition, from the one-hot encoding of a word, we can either extract the TF-IDF definition from the original term document matrix, term definition matrix, or we can extract a single embedding that we can use as we use the Word2Vec or FastText embeddings. So what's the catch here? The point is that we want to exploit the structure information, so we have a precise definition from a word that is often organized into nouns, adjectives, verbs, and so on, and we want to exploit the compositionality of vectors. Basically, we want to build the embedding for a single word, for a single term, combining together the pieces that compose its definition. Consider, for example, the word embedding. It has its own definition, and basically its representation should be a combination of the individual terms in its definition. Moreover, we can exploit also some sort of recursive structure. So once we have defined embeddings, we can add the concept of plural together with that of this word to build up the word embeddings, which is the plural of embedding. So the idea is to move from a paradigm where we study just words co-occurrence statistic to some more structured information and to define a word by actually its own definition. And this opens up for the extensibility of our model, which is the way we want to use to overcome the out-of-vocabulary limitation. So from the LSA decomposition, we have this approximate equality. It's an approximation because usually with the LSA decomposition, we truncate some of the information. And we have that the TF-IDF vector of a definition is actually almost equal, approximately equal to what you can extract from by multiplying the one-hot encoding of a word vector to the three matrices resulting from the decomposition of from the LSA decomposition of the entire term definition matrix. And we have that the first of these three matrices is our word embedding matrix. So basically we are fetching the embedding with the first multiplication between the one-hot vector and the matrix U. And the rest is what we call the definition embeddings. So it's another piece of the original term definition matrix that we can use in a different way. Also, we can move a bit the things in the approximate equality, and we can actually reconstruct the word embedding that we could fetch from the matrix U by multiplying the TF-IDF vector with the other matrices resulting from the decomposition. We can simply invert all the transformations because matrix U and V are orthonormal, and the matrix sigma from the LSA is a diagonal positive matrix. We drop all the negative or null terms from that. So everything is invertible, and we can invert the equation to do this kind of reconstruction. And the good thing is that we can introduce the definition of a new unseen word and still get an embedding that is approximately equal to what we could have got if we also train the LSA on the definition of that same word. So basically, it's an embedding point to a position very close to the target one in the space, and we can use these embeddings inside a neural network, as we always do with this kind of applications, since neural networks are expected to be robust to these reconstruction errors. And this is how we propose to approach the out-of-vocabulary issue by constructing a model that is actually extensible by starting from the definition of a word out of the vocabulary and introducing it back into the embedding space. What we did at this point after defining the model was to scrape the data from the Wiktionary dictionary, since we decided to go for this because it is openly available, continuously updated, and it also contains multiple languages, so we can eventually scale up to other languages. Up to now, we only worked with English, and we use it as a pre-training corpus to do unsupervised learning and LSA and build up our Def2Vec model. As you can see from the statistics, The vocabulary of our model is much smaller if compared to that of other word embeddings model, even the training token are. But in this dictionary, in this dataset, we have much more cleaned and controlled data, and we don't have many of the, let's call it, garbage that comes if you scrape randomly data from the web, like all the misspelled terms that you get, for example, in Word2Vec or FastText and similar. Once we trained with LSA our model, we had our reference embeddings, and we started planning the experiments. We defined two kinds of evaluations, one on embeddings quality, so we wanted to assess how good our embeddings were, and the other on the reconstruction capabilities. So we defined a separate experiment to understand if the embedding extension and reconstruction is working as expected. We took 4 different tasks, 3 from the CoNLL text labeling task, the post-tagging, chunking, and named entity recognition, and 1 task of semantic similarity, and we tested our model on these benchmarks. We built a very simple convolutional model. We were not interested in building very complicated, like transformer-based models, but just very simple ones to test the embeddings. And we used these simple models either alone or in a Siamese configuration for the sentence similarity task. And we trained them starting either from the Def2Vec embeddings or from other word embeddings like Word2Vec, Globe, and FastText for the quality evaluation. Basically, we tested on this benchmark models trained either with Word2Vec or Globe or FastText against ours. Additionally, for the reconstruction assessment, we decided to get back to the original dataset, drop all the words that were occurring 10 times or less, and refit our model via LSA. We remained with the vocabulary of slightly more than 30,000 terms, and we decided then to reintroduce the by reconstruction, so not starting from the LSA, but by reconstruction, the embeddings of all the words in the benchmarks that were missing in our vocabulary. You can see on the right the statistics, so we had a major part of, a very large part of the sentences in both benchmarks that contained words with, contained samples with missing words. For example, in the STS test set, we even had 60% of the sentences to compare that contained words that were not in the original training data of the truncated Def2Vec model. And we did all this process to compare the reconstructed, the results of the reconstructed embeddings to those of the original Def2Vec model trained with the entire dataset. From the evaluation on embedding quality, we obtained very good results, yet not comparable with state-of-the-art, in the sense that Globe and FastText consistently outperformed our model, yet we managed to outperform Def2Vec in 3 of the 4 tasks. Depending on the metric, the reference metric. So we consider mainly the area under the curve of the ROC, and in all the 3 text labeling tasks, Def2Vec obtained better results. If we consider, for example, accuracy of these classification tasks in named entity recognition, Word2Vec worked slightly better, but still the results were very close if you compare, for example, the difference on chunking or post-tagging. Concerning instead semantic textual similarity, we achieved the worst overall results with the Def2Vec model, so it's not perfect yet. We are still working on improving that part, but still we obtain results very close to at least other word embedding models. So they are not as good as what a transformer could get on these tasks, but at least is a valid alternative to other word embeddings model for many applications. For what concerns the reconstruction capabilities, we recomputed the results training a separate model with the truncated Def2Vec version, and we observed that especially on the text labeling tasks, the difference in results were very small, always less than 1% of difference between the obtained metrics with the entire model and the reduced one. Again, on semantic similarity, results were slightly worse, but Again, very close. The overall difference on the test set was 1.15% in favor of the full model with respect to the truncated one. So in the end, what we observed is that Def2Vec obtains comparable results with the main word embedding models, not state-of-the-art like transformers, but at least is an alternative to other word embedding models. It uses, even though it uses smaller pre-training data. So if you see, for example, Word2Vec, which uses, if you've seen the table, Word2Vec that used 100 billion words in the training data, still performed most of the cases worse than Def2Vec. It used only 50 million samples in its training set. It saw only 50 million tokens in its training set, while Word2Vec saw 100 billion tokens. So the quality of the training data impacts a lot the results. The extensibility via embeddings reconstruction works well. So the results were almost identical between the entire model, the full model, and the one with reconstructed embeddings. And the extensibility process works without the need for any retraining or fine-tuning. And this makes it also applicable in some domain-specific applications where we have very rare terms that have their own definition, or terms that are used with an overloaded meaning in text. And we have also space for further improvements. I'll get to there in a moment. I just wanted to point out that our model is available in Gensim format on GitHub, so you can download it. There is the link also in the paper. Concerning the next step, I will go through them very quickly. We want to exploit also subword information, like FastText is doing. We want to test different languages, and we want also to go towards more complex models. Now that we know that it works sufficiently good, we can try more complex recurrent or transformer networks and even more sophisticated benchmarks. Thank you all for the attention. If you have questions, I'll be pleased to answer.